Hello, everyone. So today we're going to be wrapping up our conversation about energy balance by focusing in on one of the most important unit operations in industrial chemistry, and that's distillation. So we're going to be doing this from a very different perspective than we did in physical chemistry, where we mostly focused in on the distillation column itself. Today, we're going to be focusing on how the whole distillation apparatus works as kind of a net whole and how it can be incorporated in other processes, and specifically some key portions of energy and mass balance, which are worth addressing. So, again, as I've been talking about frequently so far, distillation is probably one of the most important uh, apparati in the entirety of industrial chemistry. Uh, as it stands in for the vast majority of separation schemes. But it doesn't require a detailed knowledge of mass and energy balances and being able to combine these two in order to build a real operating column. So let's go ahead and talk about how a column's actually set up. So most of what you probably know about is a distillation column works by feeding in a hot liquid from which you're going to have raising hot vapors rise and a cold liquid lower. And so then you'll end up with what's called a bottoms and a distillate. So essentially, what we have to watch out for is some little pesky details. So my feed, I'm going to pump out onto a tray, at which point the more volatile liquids will end up being caught up in a vapor, which will rise till it hits the next tray, which will then increasingly become a little bit more richer in the distillate. Similarly, what we're going to find is that as our distillate rich vapor goes up, what we're going to have is a liquid rich in our bottoms flowing down. And so the real questions kind of be what's going to be in uh, each of these streams. So as we get further and further down, we're going to have our bottoms are going to be our, our, our system's going to be much richer in our bottoms, which are going to be the less volatile liquid. Similarly, our more volatile liquid is going to increasingly enrich our vapor phase. And so what we end up having is in a typical distillation column, we're going to have a whole bunch of these vapor trays. Each one is going to essentially be a point at which the falling liquid can meet the rising vapors. They'll mix, and what we're going to have is almost a gas stripping event, where the vapors are going to strip out the more volatile liquids out of the out of the liquid that's falling, which will help ensure that we have a distillate rich vapor coming off the top and a bottoms rich vapor coming off the liquid at the bottom. And again, the concentration of the distillate is going to increase the further up the column we go. However, in order to ensure that we've stripped out the bottoms out of that vapor, we're also going to find the temperature is going to decrease as I get further up. So again, what's going to end up happening is as the temperature gets cooler and cooler, it's going to be harder for that bottoms to be in the vapor phase. Similarly, if I get hotter and hotter as I go down, it's going to ensure that any of my distillate's going to want to go the other way and get out of solution. So it's worth noting that if you're really going to model a good distillation column from a chemical perspective, what we typically do is what we did last semester in PChem and use a multi-phase diagram to figure out the ratios at each of these, the ratio of distillate to bottoms at each of these trays. And this is exactly one of the ways you can examine the distillation column is by finding the separation at each tray and performing a mass balance of figuring out how much of the liquid will fall and how much of the vapor will rise at each stage. And this is actually a quite elegant solution to solving some of the problems we addressed last year in physical chemistry. And so what we're going to find is, again, the gas stream is going to be rich in the light species, but contain a decreasing amount of the heavy species the further up we go. And what we can do is assume that each one of these stages will have a separate temperature, but that these temperatures will stay relatively fixed, and this will keep a fixed amount of flux of each of these species going up and down in the liquid and vapor components. So again, assuming that if I'm trying to use distillation to separate methanol and ethanol, which is a very classic way of making sure that we render ethanol drinkable by stripping out the toxic methanol components. What information would I need to determine the flux rates at each of these stages? So this is going to be a lot of the information that we talked about in physical chemistry. So I'm going to need the temperature because that's going to tell me a lot about where I am on the phase diagram. I'm also going to need to know the flow rates to make sure that I'm at equilibrium and to, again, uh, show me how much material overall is present at the stage. But most importantly, what we're really going to need is the composition of all of the inputs. So I'm going to need to know the composition of my feed at my stage I, and then my composition at the stage above and below me to figure out uh, what's entering any given one of the trays that I'm trying to solve. However, this would be how we'd solve for each of the trays individually, but since this is more of a survey course, and we've dealt a little bit with this last year, we're going to focus a little bit more on the apparatus as a whole. So what we're going to be trying to do is look at the whole distillation apparatus and how it runs. Now, one of the things worth noting is that in order to keep this system running, I'm going to have a liquid feed coming in, but I also need to make sure that I constantly have some amount of liquid flowing down and some amount of vapor rising up. So what we end up doing is we put a condenser at the top where we take our raw vapor, we condense it down into a liquid distillate, and we pump some of that distillate actually back into the system to ensure we have a constant liquid flow. Simply to make sure I have a gas vapor, which should strip out my distillate out of the falling liquid, I'm going to need to take some of my bottoms, vaporize it, and then let it flow up. So what we end up having is a lot of moving parts to this system. And again, control valves present at each. So we've got, so what this ends up having is giving me a lot of different mass balances to look at. So let's go ahead and start by trying to figure out what mass balances are going to be present. So there's the always good old give me. We've got the total mass balance. So for the whole system together, where I've got feed entering and distillate and bottoms leaving. I also have the column where I've got feed entering, bottoms leaving, and a bottom vapor coming in. And I also have my distillate vapor, or my reflux or distillate vapor, as well as the raw distillate vapor coming out. So this has three inputs and two outputs. So this is probably the messiest of the balances. Similarly, what we often do is we encompass the whole condenser apparatus, so the condenser and the split, into a single mass balance, and the same thing with the bottoms. Though it is worth noting that while the phase may end up changing on the condensers, the actual identity composition of the system doesn't quite so much. So as a whole, this gives us four major balances that we're going to be working on. And it turns out in order to solve any single balance, you may have to solve several of the others to bring everything together. And that can be a little tricky. So let's go ahead and take a look at how we would look at these various mass balance. So again, my column itself has the column altogether has one feed and two outputs. Sorry, it has three feeds, feed, reflux, boil up, and the important ones, which I want to introduce some variables for, the distillate vapor, which I'm going to represent with a V, and the liquid bottoms, so this raw product, which I'm going to represent with an LB. Then On my distillate, this vapor can be condensed and then separated into the liquid distillate, which I'm going to represent with an L, and the actual distillate product, which I'm going to represent with a D. Now, one of the important things, as you may have noticed, is that this apparatus is so important that it's able to still the L variable away from the LB on the bottom, because often what we're much more interested in is the distillates rather than the bottoms, which very frequently are composed of waste materials. So one of the important things to make sure that you know is the reflux ratio. So this is essentially how much of the liquid I end up putting back as this reflux liquid, or L, versus the product distillate, which I pump out. So this gives me the reflux ratio R. So if you see this R variable, this is going to be telling me a lot about this various ratio. And this is going to be something that's going to be very carefully chosen to make sure that the apparatus doesn't suffer, doesn't either dry up or have catastrophic buildup. So again, choice of this reflux ratio is going to go a little bit beyond the scope of this course, but is a very important variable to know. Similarly, over on the bottom, our liquid bottoms are then going to be separated into a substream that we're going to boil to make the liquid vapors, and then a final product of, again, that bottoms we talked about earlier. Now, it's important to note that we like to extract the bottoms before we do the vaporization, so that so that I don't need to introduce unneeded heating of the system, which would cause a waste of energy. So using these variables, we can generate several mass balances. The most important, which again is the total mass balance of the system. So this is going to be my feed is going to equal the sum of my distillate plus my bottoms, because I want to avoid any accumulation or dry up of my apparatus at all costs, because we love a steady state system if we can get it. Similarly, one of the things that you can do is you can use a mixture of component and total mass balances for the system to solve the identity of what's in the bottoms and feed directly. And we've done a simple version of this total balance before. However, what we haven't gotten into is the information needed to identify what's going on in the condenser and the reboiler, which can be fairly important for examining our energy balance, because we also need to figure out how energy is entering and leaving the system, because it turns out this energy component is the major cost of running a distillation column. So we've got two major energy inputs coming into the system. The first is this feed often has to be carefully preheated to a temperature at which I can introduce it somewhere into the middle of the column. So this usually means that there's going to be some large degree of vaporization already happening on our preheated feed. Similarly, the reboiler is going to be a constant source of energy that's going to help keep vaporization occurring all along my apparatus. So this reboiler can actually be quite a substantial energy input in and of itself. However, if I've got energy entering the system, I'm also going to have energy leaving the system. So the two major places at which energy is leaving the system is, of course, in the products. So my bottoms should be fairly cool, because remember, my temperature should drop as I decrease along the bottoms. So a lot of energy will have, so my bottoms will be rather low energy, while the distillate will be relatively high energy. However, a fair amount of this energy will be lost to the condenser along the way. So again, in this case, the condenser is how most heat should be fleeing the system, as long as you have good insulation on the column as a whole. So this gives us to a big question of what are our three major energy balances for this system. So the first one is also probably the biggest one, which is going to be the total mass balance, because there's going to be some difference in the enthalpy of my feed versus my distillate plus bottoms. And this is going to give me my overall change in enthalpy. And this has to be equal plus to the sum of how much energy left via the entered via the boiler and left via the condenser. We also have the energy of the boiler itself, which is simply going to be related to the change in enthalpy of vaporizing my bottoms. Most of this energy will go into latent heat, but some may end up, a substantial amount may end up entering the system as sensible heat. Similar, we have a reverse process with the condenser, where most of the energy is going to be leaving our distillate as a distillate vapor as latent heat, but some substantial amount may go into the cooling in the form of sensible heat. So now we've just gone over the basics. Let's see how this can all kind of come together to solving a real distillation problem. So let's say I'm doing a classic distillation where I need to separate methanol out of water. So I've got a solution that's 40% methanol, and I want to get my methanol up to 90% purity. And since methanol is the lighter species, this is going to form my distillate. Similarly, my bottoms will be much poorer in the lighter methanol and will have a concentration of about 10% methanol. So I'm going to have a feed entering the system at a boiling point of 75.4. And the vapor is going to be leaving the system at about 65.4. And I'm going to end up cooling it down to cooling my distillate down to a temperature of 64. So again, my vapor ends up being much cooler than the vapor is going to be much cooler than my starting feed, and I'm going to but we'll enter the cooling column slightly above its boiling point, and I then will cool it slightly below the boiling point, but not very much, so that I don't have to worry so much about entering in excess heat. Then, using this raw distillate, I'm going to separate it out with a reflux ratio of 3 moles of liquid to 1 mole of distillate product. So I need to end up doing several major energy and mass balances in order to figure out exactly how much heat this condenser is going to remove. And this is going to be very important for me to figure out exactly what kind of condenser I need to build, such as how big is my condenser, and say how much cooling water I might need. So I gave you a whole bunch of information. The question is, where do I start trying to solve this problem? The answer, as always, is I draw a diagram. So I have a feed that's slightly richer in water, and I'm generating 2 products that are with the distillate slightly richer in methanol and the bottoms slightly richer in water. Now, one of the important things to make note of is that my bottoms and my bottom liquids will have the same composition, because there's no mixing or separation along this pathway. Similarly, my vapor and my distillate will also have the same concentration. So this is going to help make the problem a little bit easier. So if I want to try and figure out a lot of my mass balances, a lot of the information I have right now is focused in on the overall balance. So let's start by looking at an overall balance. So I know that the rate of my feed coming in has to be equal to the rate of distillate and bottoms leaving. And this is for an overall balance. So this means that my bottoms is going to have as many moles per hour leaving as my feed minus my distillate. So this is actually a fairly useful thing, but you'll notice I still have 2 variables, which means I need to hunt down another equation. So this is where our old friend the this is where our old friend component balance can come into play. So let's go ahead and balance my methanol component. So I know I've got 40 moles per hour of methanol entering the system. And I know that my distillate's about 0.9 in 90% methanol, and my bottoms is 10% methanol. So what I can do is insert my equation for bottoms in terms of distillate into this equation, which will help give me an equation only in terms of distillate. So I can then rearrange this equation to solve for D. So I end up with 0.8D equals 30. So this means that my distillate, total distillate leaving the system, is 37.5 moles per hour. So what I can do is, now that I know my distillate, I can use this to help solve for how much liquid is leaving the system, or how much liquid is being reintroduced in the system, using my reflux ratio. Woohoo! Which is which is 3. So I have 3 times as much liquid re-entering the system as I have distillate product leaving. So this is one of those things worth noting, is that often we have to be pumping in a fair bit of liquid to help keep the column itself running smoothly. So this means that I'm pumping in almost 112, over 110 moles per hour of my distillate product right back into the system to help keep it functioning smoothly. So if I know the amount of distillate and liquid, these two added together can give me the amount of raw vapor coming off of the column. So this, if I add my distillate and liquid together, gives me a total vapor of 150 moles per hour. So of that, 90% of it is 90% of it is methanol. Sorry, 90% of it is methanol, and 10% of it is water. Sorry for the mix-up there. So now I can use all of this information to try and figure out exactly how much I need to cool down this vapor by bringing it down into a simple energy balance system. So I know that I have to cool down 135 moles per hour of methanol, while only 15 moles per hour of water. So the change in enthalpy of the methanol is going to be related to essentially how much it takes me to cool down my methanol to the boiling point, plus essentially how much it takes to condense the methanol, plus how much it takes to cool the methanol down to the final temperature of 64. So if we add together these 3 components, we end up with a total loss of heat of almost a little over 5 megajoules per hour. And again, you might notice that most of this energy is caught up in this latent heat. But this isn't too surprising, as the total temperature difference in this for this whole cooling process is less than 2 degrees. So again, not too surprisingly, latent heat will by far dominate the system. However, don't forget, we also have to cool down the water. In this case, I have much less water, only 15 moles per hour, and I'm going to also need to essentially figure out how much it cools. But one of the things to watch out for this case is that my enthalpy of vaporization is given at the boiling point. So I have to figure out how much energy it would effectively take me to heat the water up to 100, condense, and then cool it back down to 64. So watch out, because each of these component numbers isn't going to represent how much energy is actually involved in the system so much, but the overall number does indeed represent the cooling of the water, with an overall energy output from condensing the water of about 0.6 megajoules per hour. So a decent bit, but significantly lower than the methanol. So we can then add together these two components. We find we have an overall energy requirement of about 5.8 megajoules of heat needed to be removed per hour. So then we need to look at what most of the uh, contributions to this heat release are going to be. So the big thing we're going to want to do is, again, compare our two components. And we'll notice just due to the sheer volume of methanol, definitely not due to its relatively lower latent heat, most of this energy actually goes into cooling the methanol, which again isn't too surprising because it's the major component. But one of the things to watch out for is that the uh, exact subdivisions of the water component aren't indeed going to be the case, because these sensible heats of water are much larger than they would be in reality, because we had to artificially use the property of state functions to compare it to 100 degrees and not the 64.7 we did for methanol. So this actually is a pretty good illustration of how we can use a lot of information about mass balances for an overall larger system to help solve for the design requirements of a single component, in this case, specifically a heat exchanger. So this brings us to the end of energy balance. However, what we haven't been talking a lot about is how to design things like heat exchangers, which is going to be involve a lot of exactly how quickly can temperature move from whatever is cooling down my distillate into the distillate itself that I care about. So next week, we're going to be talking a lot about heat transfer and heat exchange. Till then, take care.